Hi guys, welcome back to the Runtime Diaries. This is Ashley Bedford, and we are going to be walking through a brand new problem today. So this problem, I'm going to let you know very shortly what its title is, but it should probably be classified as hard. But I'm going to go walk into it very shortly. Stay tuned as we break down this interesting challenge question. We're in the hashtag 30 Days of Code Challenge with Educative. See you in a moment. Today's problem is called Maximum Area Rectangle with Point Constraints 1. And trust me, this one looks harmless until you realize how much geometry, logic, and pattern recognition it hides. So in this video, we're going to slow down, visualize it, and unpack the entire thought process step by step. So you can walk away actually understanding how to reason through problems like this, not just memorize the code. Here's the problem in plain English. You're given a list of distinct 2D points. Your goal is to find the largest axis-aligned rectangle you can make using only those points as corners. But here's the twist. No other points can exist inside the rectangle or on its edges. That means if any other point touches your rectangle, even on the boundary, it's immediately invalid. So our job is to find the biggest rectangle that's clean inside and built entirely from existing points. Let's clarify what we mean by a rectangle in this problem. Because the sides are axis aligned, they're always parallel to the x and y axis, and no diagonals are allowed. A rectangle is defined by picking two x values and two y values, left and right, bottom and top. Then the corners are automatically at these four coordinate pairs: x left, y bottom, then x left, y top, then x right, y bottom, and finally x right, y top. The area is just width times height. That's x right minus x left times y top minus y bottom. We'll be using that formula later to track the biggest valid rectangle. The inputs here are pretty small. Integer coordinates. There are no duplicates, and you just need to output the maximum possible area. If there's no valid rectangle that meets the conditions, like if you don't even have four corners that make sense, just return -1. Here's the key invariant for this problem, and I recommend writing this down. For any rectangle we consider, it's valid if and only if 1. All four of its corners exist among the given points, and 2. There is no other point inside or on its edges. That's the entire rule set in one sentence. Every optimization we make later will exist only to check this invariant faster. Let's visualize this. Imagine picking two vertical lines for your left and right edges, and two horizontal lines for your top and bottom. You get a grid-like rectangle. Now you check, do the four corners exist in my point set? And does this box contain no other point anywhere inside or on the sides? If both pass, great, that's a valid rectangle. All right, let's start with the simplest possible idea. If you're a beginner, this is exactly how you'd think about it. You try every pair of x values and every pair of y values to form a potential rectangle. Then you check if those four corner points exist. If they do, you scan through all the points again to make sure none sit inside or on the boundary. If the box is clean, record its area. This method is easy to understand, but it's painfully slow. It repeats work for overlapping rectangles and doesn't scale beyond small test cases. Let's make that concrete. Say your points are arranged in a small 3x3 grid. You pick x equals 1 and x equals 3 for your left and right. And you pick y equals 1 and y equals 3 for your top and bottom. That gives you one rectangle candidate. Then you check every other point to make sure none lie inside it. Now multiply that by every other combination of x's and y's, and you can see how the number of checks explodes. So how bad is it? If you have C unique x values and R unique y values, the total rectangles you can form are roughly C choose 2 times R choose 2. And since each rectangle scans up to n points for validation, that's O of n times C squared times R squared. Completely fine for toy data, but as soon as your dataset grows, it's going to crawl. So we need a smarter structure. The first major insight is this. Instead of checking every possible box independently, we can fix 2 rows, a top and a bottom Y, and then sweep left to right across the columns. This way, we only handle columns once per row pair. It's like looking through the world through horizontal bands and asking within this band which columns could start and end a valid rectangle. Inside a fixed horizontal band, each column of points can be categorized into 3 types. 1. Edge columns. They have a point at Y bottom and a point at Y top, and nothing in between. These can serve as vertical boundaries for rectangles. 2. Blocker columns. They have any point that sits between Y bottom and Y top. Those are walls that stop rectangles. 3. Neutral columns. They don't have any points in this Y range at all, just empty space. Once we see it this way, we can process columns much faster. Here's how the optimized sweep works. For each pair of Y values, bottom and top, we'll scan through all columns from left to right. We'll keep track of the most recent clean edge column. Whenever we find another clean edge column, we can immediately compute the area between the 2 edges, since we already know there's no blocker between them. If we hit a blocker column, we reset and start fresh. This simple scanning pattern eliminates the need to rescan all points each time. This sweep approach is both clean and mathematically correct. Each edge guarantees its top and bottom corners exist. Each blocker guarantees you'll never cross through a column that introduces an interior or boundary point. And by sweeping from left to right, you're respecting the invariant automatically, without ever needing to recheck every single rectangle from scratch. So we're enforcing correctness and saving massive computation here. Before the sweep, we'll prepare our data. We'll group all points by their x-coordinate, so for each x we store all y values seen in that column. We'll also keep the sorted list of unique x's and unique y's. Now, we can quickly answer questions like, does this column have y bottom? Does it have y top? And does it have anything in between? This tiny bit of pre-processing makes the later sweep logic effortless. You don't need fancy libraries for this. If you're not allowed to use default dict, just build a dictionary manually and use the .set default method. When checking a column, you can loop over its y values to see whether y bottom or y top exist, and whether there's a point in between. For small data, this is already plenty fast. Alright, time to talk numbers. If you build your columns in O of n log n or O of n, and you run the sweep for each pair of rows, that's about O of r squared times c total. That's orders of magnitude faster than the naive method, and in practice it runs instantly for small to medium datasets. Edge cases can make or break this problem. Corners are allowed on the boundary, obviously, but no other points can touch or cross the edges. We also reject invalid rectangles, where x left equals x right or y bottom equals y top. And if no valid rectangle exists, our answer is simply -1. Simple, predictable, and safe. Now, a few common pitfalls here. The biggest one is trying to build rectangles directly from point quartets instead of thinking in pairs of X's and Y's. Another, forgetting to reset your sweep when a blocker appears. Or getting off by one errors when comparing coordinates. Every one of those mistakes comes down to misunderstanding your invariant. Keep that invariant in mind and these bugs will disappear. Let's summarize the naive version in pseudocode. You loop over all pairs of X's and Y's. For each, check if all four corners exist. Then scan all points to ensure the rectangle is empty inside. If clean, calculate the area. Easy to follow, but inefficient. Now the optimized version. You fix two Y's, scan columns left to right, track the last clean edge column, and compute area when you find another edge before hitting a blocker. This removes the repeated scanning entirely and respects the no interior points rule automatically. On Leetcode, you might see a short, lightning-fast solution that just sorts points and checks adjacent ones. It's clever, but it's also fragile. It assumes your points line up perfectly when sorted, and that's not guaranteed. And it can miss valid rectangles or break the no interior points condition entirely. It's faster on paper, but not reliably correct in all scenarios. Our approach trades a few lines of extra code for guaranteed correctness. If you're working with thousands or millions of points and you need to repeat this operation many times, then sure, use sweep line algorithms, 2D prefix sums, or segment trees. But for single queries or small inputs, this structured sweep is perfectly optimal. So how do you apply this way of thinking to other geometry problems? Always start by drawing tiny examples. Write your invariant, what must always be true for a solution. Build a naive approach that enforces it. Remove repeated work by spotting structure. Use preprocessing to make lookups fast, and test with edge cases before optimizing code. All right, let's wrap this up. Today you learned how to reason about rectangles using X and Y coordinates, how to define and enforce an invariant, and how to evolve a brute force idea into a clean, structured sweep. Even if this problem looked intimidating at first, you now have a toolkit that works for any empty rectangle or no interior points. Challenge in the future. If you're with us, thank you so much. I hope that you enjoyed this video. If you liked it, like it down below, share with a friend, subscribe to our YouTube channel. We're going to be bringing a lot more breakdowns to you very soon. So we hope to see you next time.